Well, good morning or good afternoon, depending on where you are at, and very warm welcome to our September monthly webinar that is sponsored by the ABC UTC at FIU. I'm delighted to say that today's webinar is entitled Oklahoma Department of Transportation ABC Bridge Replacement on SH-51 over Cottonwood Creek. And we are delighted to have two great speakers with us, Randle White, who is with Oklahoma DOT, and also Jason Langhammer, who is a senior project manager with Garver. During the registration process, we did receive a number of questions, but it is not late. If you have a question during the presentation, please, by all means, post it on the dashboard. We are going to try to answer as many of them as possible. Ben Bierman will be moderating the question and answer period. We will finish the webinar no later than 10 minutes after the hour, and we will do our best to answer these questions. A couple of just update on the upcoming conference, 2015 National Accelerated Bridge Construction Conference. That is going to be held December 7 and 8 at Hyatt Regency Hotel in Miami, Florida. Please note that early bird registration rate is going to end on Friday, October 9. Please register. The registration process is fairly easy. It's online. All you have to do is go to the conference website, which is 2015 abc.fiu.edu. and register online. During the December, as you might guess, Miami is a very busy place, and however, we have reserved a block of rooms at the Hyatt Regency Hotel. While these rooms are available, we would strongly suggest that if you're planning to come to the conference, to reserve your room as soon as possible. You can do so at the special conference rate by visiting the conference website and go to the hotel page. Also, for those of you who are interested to attend, we are still accepting application for travel scholarship. The process is fairly easy. All you have to do is send the email to the email address that you see on the screen, aazizina@fiu.edu. And by first week of October, we are going to be finalizing the recipient of the travel scholarship. The ABC Award, as part of the conference, we are also going to recognize best ABC projects in several categories, as well as the most influential person contributing to the cause of the ABC. The deadline was September 15, but we extended that to September 25th, which is tomorrow. If you like to submit your nominations for the project and the ABC person, please go to the website. All the informations are there, and the forms that you need to fill out, and all the other detailed information. At this point, let me turn it to Mary Lou to share a couple of more news related to the ABC.
Thank you, Atorid, and welcome to all. The ABC UTC is hosting its second in-depth web training on November 10th from 11 a.m. to 3 p.m. Eastern. The topic is the Milton-Madison Bridge Lateral Slide Replacement Project. This topic was selected based on your interest in this project when it was featured in one of our previous monthly webinars, such as this one today. The web training will consist of 6 40-minute modules by the Milton-Madison experts for the module topics as shown on the screen. The first module will be presented by Ann Rurick with the Indiana DOT and Kevin Hetrick with Clark Dietz Inc. Engineers. Module 2 focuses on preliminary engineering and the owner's consultant oversight and will be presented by Aaron Stover with Michael Baker International. Modules 3 and 4 focus on design build bidding, ABC, maintenance of traffic, and peer rehabilitation design and construction, and will be presented by Travis Butts with Travis Butts with Burgess and Nipel Inc. Module 5 focuses on the main span design and construction and will be presented by Murray Johnson with Buckland and Taylor. And the last module, Module 6, will focus on construction and will be presented by Charlie Gammon with Walsh Construction. The presentations will each be approximately 30 minutes, focused by a question and answer session that will allow participants to ask their specific questions and have them answered by the experts. We're very excited about this upcoming in-depth web training. On-site registration will open next week. Please check the ABC UTC website. The cost is $150 per site for all 6 40-minute modules. We'd like to announce the first U.S.-hosted International Interactive Symposium on Ultra-High Performance Concrete. This symposium, co-sponsored by FHWA, Iowa State University, and the University of Connecticut, will be held July 18th through 20th of next year in Des Moines, Iowa. A highlight of the location is the close proximity to tour UHPC projects that have been incorporated into transportation projects located throughout Iowa. Abstracts are being accepted until October the 1st. That's just next week. All submitted abstracts and papers will be peer-reviewed by the International Scientific Advisory Committee. All accepted papers will be included in the conference proceedings, and authors will be required to present their contributions at the event. We encourage you to submit an abstract and be part of this important inaugural symposium. For more information and to submit your abstract, please go to the website shown on the screen. The ABC UTC has a mentoring program for its students at Florida International University, Iowa State University, and the University of Nevada at Reno, who are working on ABC UTC research projects. The program serves as a conduit for communication between the students and industry representatives with interest and expertise in ABC. We thank those of you who are currently mentors in the program, and we invite those of you interested in becoming an ABC UTC mentor to contact Dr. Brent Fairs at Iowa State University as shown on the screen. Dr. Saeed Saidi with the University of Nevada at Reno has completed a series of experimental tests under his ABC UTC research project entitled Development and Seismic Evaluation of Pier Systems with Pocket Connections and Hollow Post-Tension UHPC Columns. 3 video clips are available for viewing on the ABC UTC website under the Research tab. The presentation for next month's webinar will feature the Connecticut DOT's replacement of their I-84 bridges over Marion Avenue using self-propelled modular transporters during a weekend closure last year. The presenters will be Tim Fields, Connecticut State Bridge Engineer, Mary Baker, Transportation Supervising Engineer with the Connecticut DOT, and Mohammed Bishtawi, Transportation Supervising Engineer with the Connecticut DOT. The webinar will be held on Thursday, October the 29th, so please mark your calendars. Today's webinar features the Oklahoma DOT's lateral slide replacement of the State Highway 51 bridge over Cottonwood Creek. The presenters are Randle White, Division Engineer in Field Division 8 of the Oklahoma DOT, and Jason Langhammer, Senior Project Manager with Garver. Randle?
Good afternoon, I suppose, or good morning, depending on where you are. Jason and I are certainly happy to be here at the location to make the presentation. I'm going to have to ask somebody to get the slides. There we go. Lost the slides for a minute. Sorry about that. If you will notice in the top right-hand corner of the slides, there should be a page number. If you have a question for Jason and I, if you'll refer to that, that'll help us get back and answer that question. Next. This was the first accelerated bridge project in the state of Oklahoma. We had gone to several other states several years ago and looked at some of the accelerated bridge construction that they had been doing, but this was the first one in Oklahoma. And one of the reasons that we wanted to do the bridge slide is back in 2011, our governor, Governor Fallon, had challenged the Department of Transportation because we had a serious issue with structure deficient bridges. We were showing up at the bottom of the list for some of the worst bridges in the nation from a structural deficient standpoint. In 2011, our NBI list showed up 706 structure deficient bridges. The governor wanted us to reduce that number to get as close to 0 structure deficiencies as we could by the end of the decade. And to do that, we were going to have to address 80 to 100 bridges per year. So, we were looking at opportunities to deliver projects and expedite the construction. But we also knew with that number of bridges, we were going to have an impact on the commuters, and so we were looking to minimize that impact as well. Next. The map you see before you is of the Keystone recreational lake area. It is in northeastern Oklahoma. Division 8 is located. We have the northeastern 11 counties. Tulsa is the major city. You can see that off to the right of the screen there. The project location is about 26 miles west of Tulsa. There to the north, the Highway US 412, that is a turnpike. There are about 4,000 cars a day on State Highway 51 or the Cottonwood Creek Road, and about 15% of that is truck traffic. Next. We're looking down at an aerial view of Cottonwood Creek. The bridge at that location has a lot of patching going on in the decking area. But the interesting thing about this is that the project has plenty of right-of-way already. As you can see, it ranges from 185 feet to 215 feet on the south side or the bottom of the screen. That allows, that gives us plenty of room without having to buy any additional right-of-way to do some work, build a structure right next to that. Also through this area, the fill section, the roadway is sitting on about 40 foot of fill as well. The bridge was built, the existing bridge was built in 1961 as part of the relocation of State Highway 51 when the Corps of Engineers built Lake Keystone. The bridge is 273 feet long. It's comprised of 6 46-foot steel I-beam spans. The bridge clear roadway is 28 feet. The condition of the bridge is rated as structure deficient. The deck is rated in the poor superstructures fair, and the substructures also listed as poor. Let's take a couple of look at the couple of pre-construction photos next. This is on the roadway. We're looking to the west. The approach roadway width, we've got 2 12-foot lanes with 2 8-foot shoulders. The bridge width is 2 12-foot lanes with 2 2-foot shoulders. You can see we have substandard guardrail and substandard bridge rails there as well. And you can also see an asphalt overlay over the concrete approach slab. We'd had some settlement there, and that was an attempt to level out the bump at the end of the bridge. Next photo, this is a photo on the left is along the south side of the bridge. You can see some of the rusting that's going on the bottom of the flanges and also at the beam ends. The photo on the right, you can see again the rusting of the beams as well as some of the spalling of the deck underneath. Next. Here we're taking a look at the pier caps. You can see that we're losing some of the pier caps, some of that is spalling off. Photo on the left, you can see some rust spots just under the roller bearings. Those are some of the stirrups that are starting to rust. Next. The photo on the left shows some additional spalling and rusting of the pier steel as well. The photo on the right is looking back to the south. That's the Lake Keystone wildlife area. This is an area that the lake, whenever it fills up, backs up and floods. Next. Project goal. The map on the right basically shows what the detour would be on the state route highway system. Being in a lake recreational area, there's not a lot of opportunities to go around. But the project goal was to replace an existing structure deficient bridge. Wanted to replace it on the existing alignment. We wanted to minimize the footprint overall. Wanted to minimize the disruption to traffic. Wanted to reduce the detour duration. And this was our first ABC project, and so we wanted to evaluate that, and this appeared to be a good location. To kind of give you an idea, the State Highway 51 is a commuter route between the city of Tulsa and Oklahoma State University. There's a lot of local recreational traffic there as well, school buses, emergency. This detour is 35 miles long, and back at the time we were looking at this, gas prices were a little over $3 a gallon here in Oklahoma. They're down to about $2 a gallon right now, so a little bit of difference there. Next.
Well, for the project development process, because this was a unique site, we looked at multiple replacement alternatives, including conventional, staged, and accelerated. And for that accelerated alternative, we looked at the different methods applicable to the site, some of the risks and benefits of each of those methods, as well as putting those details in the plans, evaluated the site constraints, and then moved on to type, size, and layout. And once the department approved the preferred alternative, we moved forward to final design and construction. There are risks and benefits to using ABC methods, and the table that you see here is just some of the methods that we evaluated for the Cottonwood Creek project. The method is shown on the left, and following to the right, you have your benefits and risks. And so I just wanted to talk to you about some of these methods and what those benefits and risks are. So for SPMTs, or self-propelled modular transporters, for those of you not aware, the benefits are that you can move very heavy structures and place those structures at tight tolerances, but you do have the risk of, because of the loads they're carrying, they do require good bearing capacity. And as always, if it's not designed for and executed correctly, that moving and differential deflections could cause cracking of the deck or other members. On the other side of the table, we have EPS geofoam. Has the benefits rapid construction and reducing settlement, but that material, is flammable, will float. So you have to be careful of the site you're using it at, and may have some potential impacts due to fuel or petroleum products. So I look at a table like this is that really the methods are the tools that you have in your toolbox, and you have to use the right tool for the specific job and the site that you're looking at. There's also risks and benefits to providing ABC details in the plans, and for specifically structural placement methods, we categorize those into two types. Type 1 is where the contractor is to propose a placement method. So the contractor comes up with the methodology and then accepts all of the risks and durations that are required of the project. So the benefits of that is that you eliminate risk associated with design errors on the consulting side, but incomplete or loose specifications could result in change orders, as with any project. But one of the main things is that inadequate engineering support may lead to problems in the field. Type 2 is where a concept is defined and provided in the plans. It does have the benefit that it allows the contractor to have a biddable set of plans and potentially reduce costs. And then it provides an initial concept that contractors that may be unfamiliar with the technology, they can look at that and use that as a baseline and propose concepts that play to their strengths. And the biggest benefit that we see is that it allows the DOT to have more control over the methods used. And like any project, inadequate design details may lead to change orders, and loose or incomplete specifications could result in concepts that the client or the DOT does not want. So In our opinion, we believe that a balanced approach should be used for the Cottonwood Creek project. We chose type 2 that really provides a lot of benefits to the DOT, and on the design side, we made sure that the specifications and details were taken care of. So specifically for the Cottonwood Creek project on the structural placement methods, we looked at 3 different methodologies: off-site construction, where you construct your spans off-site, move those spans into the area with an SPMT, and then longitudinally launch those spans over the creek. It does have its advantages. One of the major disadvantages of that is cost, because combining 2 complex methodologies together is very expensive. We also looked at off-site construction of the spans, and you move those in with trucks, and then you could crane those in. Because of our site topography and the requirements, that was not really a practical application. Adjacent construction and a transverse slide really have the advantage of cost and simplicity. Along with that structural placement method, we wanted to look at accelerated substructure methods as well to expedite the entire project duration. We looked at constructing the substructures underneath the existing bridge, which has the advantage of a conventional style of construction, but it does have the potential issue with limited overhead clearance and constructing those foundations underneath an existing bridge. Also looked at precast columns and caps, which was applicable as well. But we settled on constructing deep foundations outside the existing structure footprint, and the pier caps underneath the existing bridge, primarily because it minimizes the impact on the existing users. It is conventional construction that contractors in the area are familiar with, and it provides the easiest construction. So in summary, that transverse slide methodology was chosen primarily because the site is not really conducive to self-propelled modular transporters. We do have poor soils in the area, and as Randle mentioned, this is backwater for Keystone Lake, and there is potential flooding. The SPMT plus a longitudinal launch combined is very expensive. The site does allow for temporary works because we do have relatively shallow bedrock here for foundations. The accelerated substructures were applicable as well because we do have a relatively narrow bridge, and we could do all of this while maintaining hydraulic adequacy and freeboard. Some of the design considerations for substructure placement and for the permanent substructure design is how we're going to account for fixity, expansion, and contraction of the bridge in its final condition, even though we have to move the span separately or together. As far as the slide itself, do we want to push it or pull it? And of course, we're dealing with some very heavy loads here that need to be accounted for in our loading combinations. Sliding systems is also a very important factor in considering the methodology, as well as your sequence of construction to make sure that this project is constructible and that the goal of the project to accelerate the project is achieved. So for substructure placement, most of you are engineers. You know that placement of your spans, the span length, and the structural depth are all interrelated. And so we try to balance those 3 items in order to avoid conflicts with the existing or the proposed structures, maintain hydraulic adequacy, and as always provide that constructability. Here in the bottom of your slide you see the existing bridge that is dashed and the proposed bridge that is solid. So for the pier design, as I mentioned, we constructed those underneath the existing bridge. In the elevation to the bottom of the slide, you can see where our proposed low beam was relative to the existing. What you're seeing here on the left-hand side is our proposed pier relative to the existing superstructure. We had about 4 feet of vertical clearance between the top of proposed pier and the bottom of existing superstructure, primarily because we used a larger structural depth superstructure, which allowed us to have that constructability. The existing bridge width, 32 feet, as Randall pointed out, and because it does have relatively narrow width, we were able to construct outboard drilled shaft foundations. You can see the proposed pier in plan view highlighted in red. And as always, for pier design, we had to account for vertical, horizontal, and torsional loads. Now, I want to show you a section of our pier. If you take a look at the elevation view and were to cut a section through that proposed pier, this is what you would see. And so because of that relatively large span over or underneath the existing bridge, we had about 45 feet. We chose to look at a T-beam design. We looked at both rectangular and the T-beam. The T-beam, of course, was more efficient. And not only do you need to account for your permanent loadings, but vertically and horizontally and torsionally, but you also have to look at your temporary load cases because we did not specifically specify which span was to slide first. We wanted to give that flexibility to the contractor so they could organize their sequence to reduce the overall construction time. Here is an elevation view of the pier, and you can see the blue lines illustrating the reinforcing steel. As I mentioned, the 45-foot span, quite larger than normal, and because of the T-beam design and the relatively large loads sliding from the temporary substructures to the permanent, we had to have some pretty tight spacing on our stirrups for the torsion and shear. And so that's one thing to keep in mind when you have heavily reinforced structures, and of course you can't pre-install the anchor bolts, is how are you going to account for the contractor to place those anchor bolts? So constructability was the main concern here. For the abutment design, similarly, we constructed those underneath the existing bridge, and as you can see from the elevation view, and we're able to do that with the use of a soil nail wall. You can see the red lines in the elevation view now. That's where we constructed those soil nail walls, and those walls really serve three different purposes. It served one to keep the existing structure stable, two to provide an area of excavation for the new abutment, and thirdly, it helped to reduce the amount of lateral pressures that the proposed abutment would see. Constructability is always a major concern, so here's kind of a picture showing where that excavation would be. We only had about 11-foot headroom, so it's always important to make sure that there's equipment available to construct that wall within the tolerances or the site constraints that you have. So on the right-hand side, you can see the embankment. The dashed line, again, is the existing structure, and I'm highlighting a blue line there, and that's where the proposed soil nail wall was constructed in front of the red proposed abutment. And as I mentioned before, design for lateral earth pressures was a major concern because of the configuration of the abutment, and so that soil nail wall helped reduce that. Here's an elevation view of the abutment itself. You can see where the high water mark would have been. Because of that span underneath the existing bridge with outboard drilled shafts, we had a relatively tall cap and a relatively tall superstructure in order to lower our proposed low beam. So there was quite a bit of lateral earth pressures that needed to be accounted for. As far as sliding systems, there are manufactured systems. They do require relatively shallow grades, but they do have very low friction. The picture in the upper right shows one of those systems where it uses a standard MC steel shape and is really a guided track type system, and of course the beams have to be connected together, and the illustration to the bottom of the slide kind of shows that type of roller system, and in this case we have showing a post-tensioning jack, and in essence this is really a very large drawer slide. Each one of these rollers is articulated. Here is the underside of one of those rollers. Kind of has a rolling caterpillar track that you're used to seeing on heavy equipment, but each one of these cylinders also has a bearing, and that's really what provides the low friction and greatly reduces the amount of force that you need to either push or pull that superstructure into place. There are contractor-developed skidding systems out there that use low-friction materials or lubricants. In the case of Cottonwood Creek, we had specified a roller-type system, but allowed the contractor to propose new methods. And we believe that proposing or specifying a system at a minimum and allowing approved equals, it really set the bar. And so it gave the DOT justification that if a system they didn't like was proposed, we had one that was specified in the plans and specs. Here's an elevation view of how that articulated roller system would look underneath a beam. So I want to walk you through the planned construction sequence. Here's the existing bridge, 6 at 45, as Randle pointed out. And so what the first stage of construction would be to install those soil now walls and perform that excavation. At that time, the contractor could go ahead and construct the piers underneath the existing bridge. At that point, the abutments can be constructed. Following that, we have the temporary supports being constructed. From there, the beams can be set, the deck can be poured, and at that point, you're really ready to move the superstructure itself. So you could close the road, demo the existing bridge, slide the spans into place, remove the existing substructures, and then perform your final grading, and then open it up to traffic. Got a short video here that kind of illustrates that scenario in a little bit more detail. There's the temporary substructures going in, beams and decks being placed. Closure of the road, removal of the existing bridge and substructures, sliding the spans one at a time, and then removing the temporary substructures, opening it up to traffic. Some design and construction suggestions from a designer's perspective in regards to plan preparation and the design of ABC. You always want to use the site characteristics to your advantage. In the case of Cottonwood Creek, we had more than adequate freeboard underneath the existing bridge, which allowed us to use a longer spans, deeper structural depth, and to construct those substructures underneath the existing bridge. So it worked out in our favor on this project. Always want to balance innovation with owner preferences in mind. As an example, bearings, if the department wants to use or is accustomed to using a specific type of bearing, and we try to accommodate that, and in the end it's going to reduce costs overall because contractors are used to those specific materials and methods. Always want to provide a concept to set the bar, and that way what the contractor bids on is clearly stated. And in regards to what they bid on, we want to be very clear and concise about payment. And there's specialty operations and equipment that's required, and specifications and plan notes are extremely important so the department does not receive change orders and additional costs that were not anticipated. As far as the specifications and submittals, design requirements for temporary structures or even permanent structures if that's the case on that particular project. In Cottonwood Creek, for instance, the temporary substructures requirements were given to the contractor because we thought that they might want to use some materials that they had on hand and that could reduce overall costs of the project. But it's very important if those responsibilities are left to the contractor that the requirements for the design of those substructures is very clearly stated. Specialty equipment specifications is very important. And in the case of structural placement methods, those tolerances of those superstructures is very important and different depending on what type of placement method that you're using. Always want to allow for innovation. Contractors are out in the field every day a lot more than engineers, and they understand the equipment and the ins and outs of what's going to save time and money. And then on bidding, always want to require qualifications. These methodologies are highly specialized, and if a contractor has not performed these operations in the past, requiring them to have a technical expert on site and on board is very important. And then lastly, to provide incentives and disincentives.
Thank you, Jason. Now let's talk a little bit about the construction costs and comparisons. We looked at, obviously, an accelerated bridge construction alternative, looked at conventional construction, and also looked at stage construction. The table below shows that the duration for the ABC construction would be about 3 weeks. The conventional construction would be about 6 months, and stage construction, or half of the time, would be about 9 months. The user costs were the lowest for the accelerated bridge construction. The highest at $3.6 million was under the conventional. That was, the detour, 35-mile detour around. Construction cost, the conventional method was the lowest cost at $1.6, $1.7 million, and the ABC was the highest cost at about $3 million. Looking over at the total cost, the accelerated bridge is in the middle between the stage construction, which was $3 million, and the conventional construction, which was $5.3 million. The department chose to go with the ABC project, not only because we wanted to venture off into the accelerated bridge construction, but we were looking at it. When you talk about 3 weeks closure time, detour time, versus 6 months against the total closure of a conventional method, versus doing it half at a time, 3 weeks versus 9 months. The half at a time, certainly there's a lot more exposure for the workers and the traveling public in the work zone from a safety standpoint. Whereas if you, with the ABC, you're building off-site next to it, traffic continues as normal, and it seems to be safer for both the workers as well as the traveling public. So that's why we chose to go, was basically from a time frame standpoint and user cost and safety. Let's take a look at some of the construction photos. Photos on the left, you can see the steel cages for the drill shafts, the outboard that Jason was talking about, underbuilding or outboarding as the structure was being built underneath. The photo on the right, you can see the pile bents for the temporary structures, and you can see one of the permanent substructures that's been built underneath. One of the things when you're looking at this, you need to make sure that your temporary structure you're building on is sitting on solid foundation. Make sure it's suitable, for the superstructure that you're building. Also, you want to make sure that you don't have any differential settlement or deflection. There's a lot of issues that you have to contend with, when you're moving a large structure like this and building it in the field. Next photo shows the completion of the soil nail wall that was put in to keep the existing structure stable so that traffic could remain on it. That clearance between the bottom of the beam and the ground is about 11 feet. One of the things Jason did mention is that you, as a designer, you do need to do your homework up front to make sure that what you are designing is constructible and compatible with the equipment. You want to make sure that there is equipment that's capable of accomplishing that. Next. Here you can see the substructure for the new bridge that is built underneath the existing bridge. Also, right next to it, you can see the piling for the temporary structure, and there's a connection in between the two there that is critical that you make sure that the transition, as you slide the bridge from one side to the other, you've got to have really tight tolerances on that, and you've got to make sure that the top of the cap is smooth and level, so that your bearing stresses are equally distributed as you transfer across there. The other thing to look at are the steel beams versus the bulb tees. You can see the difference in the structural depth. This is what allowed us to maintain basically the existing profile grade without having raise that up. It allowed us to underbuild and slide the bridge into place. Next. The photo on the left shows the new superstructure built in place right next to the 1961 structure. Just kind of gives you a little idea of how close together they were built. Photo on the right shows that the bottom section there shows that that section is started to move or being slid into place. You can see the piers out there in the middle where the contractors continuing to work on the removal of the piers as they're sliding one of the sections out. This slide just shows continuation of the contractor working to remove the piers in preparation of sliding. Photograph on the right shows you another picture of the temporary structure that's supporting the new superstructure, as well as the new substructure that's waiting for the span. Next. The photos here show on the left show the pancake jacks under each of the beams. Their contractor is preparing to lift one of the spans up. It's important that the jacks are coordinated so that they lift in unison. They'll raise the structure up vertically. And I guess over here on the other side, the right photo, that's the track, the white track there you see. There's a joint there that laying the tracks together. The white material kind of reminded me of the furniture sliders that you have around the house. And then the contractor used a liquid similar to a dishwashing soap that on top of the track, and then they had a sliding shoe under the beam that once they got that raised. But once they got everything into place, they would slide the beam over to the new structure, put the jacks under, raise it again, take the track and the slide materials out from underneath, and they'd install the bearing assemblies and anchor bolts, and then set the bridge back down on top of the bearing assemblies. And again, it's very critical that the tolerances are really tight and that your pier cap's level. This is a photograph of a worker connecting the threaded rods that are used as part of the pulling system. Those threaded rods are about 3 inches in diameter. The photograph on the right shows the jack that was used to pull the slide, or pull the section from the temporary location to the permanent location. They would have one of these jacks at each end of the span on the new substructure. The jacks would pull the span roughly about 3.5 to 4 feet per hour. They were able to move the one span in a day. This photograph, if you look at the top of the deck there, that little gray metal thing you see is your expansion joint there. Those were built, constructed on the with the new superstructure in place on the temporary supports, and once they moved into the permanent location, then you come back in and put your neoprene membrane in and complete your expansion joint there. And these joints do accommodate thermal expansion. Next. This is a photograph just looking at the end of one of the slides of the spans. You can barely make out on the ends the two jacking locations that they're using. One of the other things too, Jason, can you go back to that slide, please? If you look at this pier cap closest to you, you'll notice that there aren't any anchor bolts sticking up. The contractor used inserts. If you remember the rebar layout that Jason showed, they were on 6-inch centers, so it was really tight there. You couldn't really put your anchor bolts in and still accomplish the slide. So it was real critical that they located the anchor bolts, the inserts for the anchor bolts, prior to the slide, because once you made the slide in there, you really didn't want to be drilling in and cutting a lot of that rebar or anything to try to set your anchor bolts. Contractors successfully completed 2 slides. They're getting ready to slide the middle span or the last slide there. Next. And this is showing the bottom side of the anchor assemblies, the anchor bolts in place, the new structure sitting on the new substructure. Next. These are just a couple of views of showing the contractor in there removing the temporary structures. The new bridge is in place, and they're getting ready to open that up. Next. Contractor's been in, cleaned up the area. They're ready to turn traffic onto the new structure. Just wanted to let everybody know that the contractor for this project is Manhattan Road and Bridge. The contract award was $3.4 million. We did have an incentive disincentive on the project for a road closure. We allowed 21 days maximum, and the incentive disincentive was $20,000 per calendar day. And let's go to the video. The road was closed down on September 15th, 2014. Road was opened back up September 25th. Total closure time of 11 days. Contractor earned $140,000 incentive on that. Now I think I'd like to talk a little bit about lessons learned. Basically, you know, anything new is unknown, so you've got to get buy-in from top levels, your boss, industry partners, the public. Two of the big takeaways from this on this lateral slide, we were able to minimize the traffic disruption from a number of months to just a number of days. So we felt pretty positive about that. And also the work zone was greatly improved, the safety for the workers and the traveling public, because the lateral slide allowed the bridge to be built adjacent to the existing bridge instead of under traffic. Next. Another one of the lessons learned, we needed to make sure, you know, since we were building off-site, we needed to make sure we had adequate roadway tie-in links. You know, obviously the thing that you don't want to do is build a nice brand new bridge and have a bump at the end of the bridge. You want a smooth ride, and we got a very smooth ride on that. We were really pleased with that. Next. You heard us talking about tolerances and measuring things and that type of thing, and if you look here, you can see in the middle there that little plastic looking deal that's rolled up, and what's happened, there's a little bump there that kind of got the sliding sled off center with the track, and it started peeling up the track, so the contractor had to stop and cut that out and you know, get things back on track. But you know, basically you're going to have, you know, things are going to happen, and you're going to have to be ready to adapt and adjust and you know, get on down the road. So, next. I don't know if y'all have cliff swallows in the rest of the nation, but we certainly have them here in Oklahoma. Basically, what they do is, if you know, they come out and nest on your project, they'll shut you down from April through September. The thing that was kind of unusual about this was we had a steel structure, and we didn't notice any nesting on the steel structure, but as soon as we built the new concrete structure and had the formwork there, the birds really started seemed to love that, and they, as you can see, they built a lot of nests there. This project was shut down from May 2014 through September 2014 for the nesting birds. The thing that we feel very fortunate about is that this structure was built parallel to the existing road, so we were able to leave the existing road open. We didn't have, you know, we hadn't already taken out the structure, so it did not inconvenience the public. One of the things that had we not had the structure built on the side, this closure probably would have added another 5 months to the construction time. But what we learned about that is, if you build it, they will come, or they will nest. Next. Another thing, lesson learned, was you need the right site conditions, you need the right timing, and you need a whole lot of luck. We had gone through a couple of years of drought conditions, and the photograph on the left basically shows you what was out there when we were building the project. The photo on the right was it was that following spring after we completed the construction. You can see that we had some really a lot of rain, and the lake did back up, and so the consultant did a really good job about estimating the high water mark and getting the structure up out of the water, but that's right about where the estimate was. One of the other lessons learned, conventional structures are built to really tight tolerances. When you're moving a structure, the tolerances are going to be even tighter than what they are in conventional structure. When you're dealing with an ABC project, good suggestion would be live by the woodworker's golden rule: measure twice, cut once. Can't emphasize enough: check, double check, raise the red flag if you see something that doesn't fit. Next. This is our executive director for the Department of Transportation here in Oklahoma. It's Mike Patterson. One of the you know, basically, whenever you do something for the first time, you need to expect increased attention, not only from the traveling public, industry partners, but also your boss. They'll come out and spend a day with you. And the last lesson that I learned was take steps to document all stages with videos and photos, because you never know when you're going to have to be given one of these presentations. And I think that's it for us. So if y'all have got any questions.
All right. Thank you, Randle, and Jason, for a great presentation. Very interesting projects. So at this point, we will turn it to Ben Bierman, who is going to moderate the question and answer, and we will stop at 10 after 10.
Okay, can you hear me? Okay. All right. Hello?
Yes. Yes.
Can you hear me okay?
Yes.
Okay, great. Okay, folks, so we received about 25 to 30 pre-webinar questions and about 15 to 20 questions during the presentation. Randle, Jason, you guys did a great job. I grouped the questions into about 5 or 6 categories. We've got questions related to planning, cost, foundations, construction and design and detailing. So with that, Randall, Jason, let's go ahead and get started here. The first question is, you talked about the type 1, type 2 classification of, the approach on the level of detail of what you would do to develop your contract plans. I believe type 1 was the contractor's responsibility to define the means and methods, and of course the type 2 method was you would sort of define the concept or dictate a concept and kind of be opened up to other ideas. So in regard to the sliding, was it up to the contractor to modify and stage that setup himself? I mean, what type of level of detail did he need to go into to finalize this temporary staging, or temporary shoring in this case, in order for it to be approved for construction and in order to move forward? Randall, Jason, are you all there?
Yeah, Dick, you want to go ahead and answer that?
Sure. If I understand the question correctly, it's what responsibilities that the contractor had in the temporary substructures and the design for those, as well as the sequence. And as mentioned in the presentation, yes, they were required to design those temporary substructures and come up with the sequencing plan themselves as far as the submittal acceptance on those substructures. It was a back and forth process with that because of all of the requirements for temporary structures as prescribed by AASHTO. So that was your standard submittal and review process. And then as far as the sequencing is concerned, we left it open to how they wanted to slide the spans into place. We didn't specify that because if they wanted to slide 2 spans in the place at the same time and then the last span, or even all 3 at the same time, they could, if that's what they felt they could do, while still meeting the contract and specification requirements to reduce the overall duration of the project and the closure of the road.
Okay. So as part of that submittal, or really part of the contract plans, was there a requirement that the contractor's temporary works engineer be on site either for or during the move, or even prior to the move, to sign off and approve that the shoring was per contract plans or per his submittal package?
Yes, the contractor actually designed these temporary substructures in-house, and they were stamped and sealed for an engineered false work scenario, and they were on site to inspect and make sure that they were constructed according to that plan.
Okay. Here's a question regarding the approach in the backfill. What kind of details or what was used for the backwall in the approach lab to minimize the road closure? Was that conventional poured in place approach slab? Was it precast? Were there any unique details for that abutment tie wall, abutment tie-in to the approach slab?
And what do you want me to?
I was going to say the approaches were pulled out and backfilled and replaced as part of the during the slide as well. The contractor was working on that.
Okay. Let me ask you this, and we're kind of in the planning group here of questions. Was there a clear picture from past seasonal weather records that provided assurances of the waterway's low flow and high flow conditions? And were there any provisions in your contract for unseen high water impacts that would impact the project and the project schedule?
I don't know that there were specific high water special provisions, if you will. I mean, we have standard contract provisions that deal with weather-related issues and delays, you know, similar to what you'd have with a winter shutdown or something like that.
Yeah, and when, as part of this contract, did you all separate in the bid items the temporary shoring and jacking system, or was that lumped in with the superstructure cost?
The slide system with the jacks, that was a separate cost.
And was that the payment of that particular bid item? Was it done after the bridge was moved, or was there sort of like, okay, a substantial completion of the temporary shoring and jacking system is ready to go, make payment. Once the bridge is moved, we can do a final payment on that. I guess it's sort of a, was there a sort of a progressional payment provision for that item there, or that activity?
I mean, it was a progressive payment as far as, I mean, you know, they weren't on site that long. I mean, you know, our pay periods are typically every 15 days, so they got the work done in 11. So.
Okay. This question sort of on the bridge type in weight and things of that nature. There was a multiple of questions related to the weight. You know, why would it have helped to use perhaps a lightweight aggregate for the deck? Would it be beneficial to use steel beams versus concrete beams? And again, this is all related to weight of moving the spans and the jacking system required to move the bridge. Did you all go through that decision-making process and decide, well, does it make sense to use something lighter, or we don't see any deltas in the cost, or what have you?
I'll let Jason answer that.
Yes, we did evaluate both you know, steel beams as well as other types of materials. One of the advantages of a transverse slide is that you are either building temporary or permanent substructures that obviously can hold the weight of superstructure. So the weight isn't necessarily a critical item for a transverse slide, at least it wasn't in this case. One of the advantages of using concrete beams in this instance, and specifically ash-toe bolt T type beams, is it had the appropriate depth for us to lower our bearing elevations and construct those substructures underneath. And since weight wasn't a factor, and to create that structural depth, it would have probably been a little bit inefficient for steel. That's why we chose to go with prestressed concrete.
Here's a couple questions about the substructures pier caps. Yeah, I'm going to kind of group them here. There were a couple questions as why is it so deep, and I think that's obvious because it's reinforced concrete. But there were questions or comments in terms of the layout. Were there any considerations to perhaps inverting the T, use the T cap, perhaps inverting it, and perhaps to include pre-stressed or post-tensioning? And then another one that related to that as well is since it is a two-column foundation, is to perhaps put the foundations on a 90-degree instead of a skewed angle to the superstructure, and to get the span of the pier a little bit less. Were there any considerations to any concepts like that? Or was it something to where you all saw that it really wasn't something that really impacted the overall constructability or cost and layout of the structure there? Jason, I think that one would go directed towards you, being the designer of record.
Yeah. We did think about inverted keys and post-tensioning, and again, I think those are things that from an engineering standpoint are applicable. It kind of goes back to owner preferences and the typical construction procedures and methods that are done in that local region to allow more availability of contractors. And so inverted T's are not done a whole lot in Oklahoma. Neither is post-tensioning, so that's why we went with the traditionally reinforced pier cap. And as far as the skewing, yeah, the 20-degree skew did create a little bit more of a span in between the piers, but it wasn't significant enough to change the layout of the structure as we had determined it. So that's why we chose to go with skewed and place our span so we missed those existing substructures.
Okay. Well, I'm going to jump into the construction group of questions here, kind of shift gears a little bit. How was the existing superstructure removed?
When they closed the road down, contractor just came in with the equipment and took the deck out and removed the beams, and they came in with the hydraulic hammer hose and took out the piers.
In time frame, you mentioned that it took about a day to move one of the spans. Does that also include the demolition time frame to remove that component?
The 11 days that the road was closed, that included removal of the superstructure, the substructure, the approach slabs, sliding the bridges into place, striping, getting the guardrail in place, and opening it back up. That was everything.
Okay. All right. And so regarding the track system and the rollers, were those removed after the slide? It looks like they were, or were there some components that were left in place?
I was going to say once they got the span to the location, they brought the jacks in, raised the structure back up, removed the tracks, and then they came back in and put the bearing assemblies and the anchor bolts in place and set the beams back down.
Okay. And then just kind of getting more into the detail, this was on slide 27. The question came in, it appears that the roller nest were skewed to the girder center lines, and then you had the concrete diaphragms. Were the diaphragms adequate to maintain the structure's geometry during the move? And what was done out in the field to keep everything aligned while the bridge was being slid over? Were there concerns or issues with the skew angle? Did that create any problems? What were some of the techniques that the contractor used out in the field to keep everything lined up?
Say the contractor took their time during the slide. I mean, it wasn't something that was rushed. They had a lot of folks out there crawling around the structure, looking at it, making sure that there weren't any issues. Jason, do you have any comments?
Yeah, and this kind of relates to the potential for deflections and cracking and whatnot. So there was some very tight specifications on the levelness of not only the temporary and permanent substructures, but of course there's going to be variations. It's very hard to place concrete exactly level. So the remainder of the differences that were cast that needed to be made up in the actual track system themselves was accomplished through leveling concrete and whatnot, and it had to be measured and documented and prior to the actual slide itself, and that's how a lot of those deflections were controlled.
Okay. This was a question regarding closer to the abutments. It was on slide 22. I don't know if we can go to the picture, but if not, that's okay. I think we can visualize it. What method was utilized to consolidate the concrete in the abutments around the steel and the saddles in slide 22. And I guess that picture showed sort of the existing bridge and you all coming and building up under the existing superstructure. And you could see that there was definitely a vertical clearance, you know, maybe a concern there of how do you get all that concrete in there and how do you get it in there consolidated and properly built. I believe it was around, it says here slide 22, you might have to come either before or after a couple photos there, a couple.
Well, the concrete was consolidated in traditional methods. We made sure that we didn't have reinforcing steel closer than 4 inches, met the requirements that you would for traditional concrete, although it did have more reinforcing steel than what you would typically have, but contractor primarily used traditional methods.
Any special mixes like a self-consolidating or Suedo self-consolidating concrete mix, or was it just conventional concrete with the low slump and vibration, conventional vibration?
It was, you're right, the conventional vibration, and Oklahoma DOT specs does require or does have a range of acceptable slump. And in this case, I'm not aware that they tried to propose something outside of the normal specification.
Okay,
something
great.
we can check with the residency on and see if they used any special mixes. Don't
Okay.
know that we have that answer right now.
Okay, well, I've got time for one more. There's still a lot of great questions here, and what we'll have to do is perhaps just post those onto the website after we get done with the webinar session. But this one will go out to you, Randle. So this was a great ABC project. What's the ABC outlook for Oklahoma DOT moving forward?
I think we're just we're going to be looking in the future for the location that where ABC makes sense. This, and it's going to be site specific. This one happened to be we had existing right of way. It was a good place for us to make a test run at it and see how it worked. We were really pleased with the way it worked, and our bridge engineers are certainly looking forward to the next one.
And your contractor after the job, any feedback from him or her?
I think the project went really well as far as they were able to get in and do the work. They earned an incentive on the project. So I think all in all, from the standpoint that the department, the consultant Garver, and then Manhattan Road and Bridge, it was one of those things that everybody worked closely together to make sure this was a successful project. And the fact that the contractor was able to get the work done in 11 days and get it opened back up, it really was a good project, and things did go well. Everybody worked well together.
Looks like a great job. Okay, so with that, Randle, Jason, great job. We're going to pass the baton on over to Adirod, and we'll let him give us a closeout. So, Adirod,
right
to you.
Thank you, Ben. Thank you, Ben, for moderating. Thank you, Randle and Jason. Excellent presentation, very informative. And thank you all for being with us again for our September webinar. And by that note, we will conclude this webinar and hope to have you again next month. Thank you.
Thank you.